Hello, YouTube viewers. Welcome to my show, Rocket Monday. In today's episode, we're gonna talk about Parker Solar Probe. So let's dive right into it. Well, first we have to understand what the heck we are talking about here. Well, we are talking about NASA's robotic spacecraft, and the project, the whole idea was started in 2009 and it was launched in basically August 12, 2018. The total project is estimated around $1.5 billion. So it's a big mission because there are missions in different scales. There are missions that are like, always above $1 billion. There are missions that are like test mission, like that is $200 million. So there are always missions in different categories. This is a big baby, and that is the reason why people hate James Webb Telescope, because that's 10 plus $1 billion. So this is the mission, and the tagline of this mission is very interesting: a mission to touch the sun. So let's dive more into it. Well, every mission is directly defined by what kind of instruments it has. Well, this is one interesting thing. Sun has so much light that you simply cannot use optical measurements on it. Like, especially if you get close to it, you simply can't use it. So we use different methods to analyze it because it has a giant sun shield to make sure that it does not get roasted. So how the heck you observe it? Well, you observe other aspects of it. It has antennas, fields, and all that, all those things. So primary tool is electromagnetic field investigation. Now think of this way: all we are observing is magnetism, electricity, charged particles, and all that. So those are generally spread out through a large what we call energy level. So some are very weak, some are very strong. Now, so we have one of that. Then we have integrated science investigation of the sun. Now the actual name of that would be ISIS, but again, because of the political reason, it was renamed to ISOIS. O standing for the sun, so you can understand that politics happens. Now then you have wide field imager for solar probe. Now this is the first thing. If you type solar probe video, you will get that. It's generally these two cameras. There are two cameras facing sideways. So basically, if I'm looking at the sun, the camera is facing this way. Now the reason for that is it's going so close to the sun. Basically, it can directly see solar storms. It can like just look at it. It's like, yeah, solar storms are happening, and giving looking at this vantage point gives them certain advantages, like how the heck it interacts with other environment. That is why there are two, and it's quite basically beautiful, but black and white. Then we come to solar wind electrons, alpha and protons analysis system. Now why the heck we want to understand alphas and protons and all that jazz? What, think of this way: there are three energetic particles, alpha, beta, and gamma. Now alphas are very weak, so by the time it reaches to earth, it's almost destroyed. So if you are going close to it, then you can observe them. And this is the one thing: if you want to make a clear picture of something as complex as a star, you have to analyze every single aspect of it. One of them is low energy particles also. So that is why we want to understand what the hell alpha is also doing there. Then we have the grand total of that: heliospheric origins with solar probe plus. Yeah, that's a very weird name. So the total idea is that using this, because we are going so close to it, is closer than anything we have ever seen center there with modern instruments and all that jazz, is that we're gonna get a much more accurate picture of what the hell is sun, like how the heck it works. Because to give you a simpler context of how complex sun is, if I tell you magnetic poles of earth, you will think north up, south down. Okay, awesome, everything cool. Can you apply that to the sun? Short answer, no, because it will have north pole, another south pole, another north pole, another. It's like, it's literally, the plasma is interacting so violently. It's literally having magnetic field that is stretch, and then it snaps, and that snapping is what causes what we call coronal mass ejection. So you can understand it's a completely different beast, and it's a nuclear reactor going YOLO. So it is very violent. To understand it, we have to understand much more about it. We can't just understand it from Earth. Why? Simply because even though it's very bright and very powerful, due to the distance, we can only observe big things. We can't observe small things. It's like if you have a telescope and you're looking at a forest, yeah, you can see the big trees. You may be able to make out which kind of tree it is. But if I ask you about a plant, a small plant, you can't study it because of the distance. So how the heck is going to travel to the sun? Now this is one very counterintuitive thing about sun. Going close to it is very difficult. You may think, oh, it has a gravity, it will just suck you in. That's not how it works. So basically, that is why Mercury has a ludicrously weird orbit, and we don't want to crash into sun. We want to observe it. So we want to be in orbit, hopefully for multiple years. So we had to do a lot of clever engineering. Now the first step of that engineering was get as much delta V, aka velocity, as possible. So we used a ludicrously large rocket for it, delta 4 heavy. As you can see that, like, this is a tiny probe and that is a giant fairing. It was like oversized. The rocket was oversized. Now again, it had to be that because we needed a lot of velocity. then that alone will not do anything. That will only send you through the sun, through as in like sun is here, it's gonna do this. Now here's the, you're gonna go straight away, or if you do very close, you're gonna get backed out. However, we timed it such that it's gonna while it's returning, basically Earth, we sent it. It went to the sun, made a turn around. By the time it's coming around to Earth again, it will get encountered by Venus, and Venus gravity is gonna pull the orbit shorter. So basically, the orbit will be like first orbit, whooey, the second orbit like 12 smaller, third orbit even smaller, fourth orbit even smaller. That's the reality. That's what we are trying to achieve. Now we're gonna do 7 flybys to Venus. So far, 2 have already been completed, and each of them takes roughly a year. So each time we are doing it, we are getting closer and closer and closer and faster also. And when we are talking about the orbit kind of thing, basically it's heliocentric. We are orbiting the sun, it's very elliptical, and during a descent to the sun itself, we're gonna get yo-yo speeds. I'm talking the fastest man-made object, as high as 200 kilometer per second. That's fast. So that's how we're gonna travel to it. Now, then the question becomes why we are spending $1.5 billion and all that jazz, the usual BS. So the reality is very simple. Sun is very important. Now, sun is so important that people who study basically weather patterns, like cyclones, tornadoes, and all that, they also have to account for solar energy input. Now, sun for you and me is just like, yeah, it's hotter in summer, it's colder in winter. But in reality, if you like analyze it above from Earth's atmosphere, it is very violent. Like the energy output, yeah, it's quote unquote constant. It's like, yeah, like this, but it's like, so if you can analyze those parts, you can accurately predict where the storm is gonna form, where the cyclones will take their energy from. Because again, sun is the only energy source on Earth. There, like unless you are counting nuclear reactions, there is only one source of energy. Be it even fossil fuel comes from solar energy. So that's the reality of it. If you understand the sun, how the heck it's interacting with the subsystems of Earth, you can truly predict Earth itself. That is why now sun, because it being so far, and whenever you type sun images and all that, you will see something like this. Now this is quite amazing, quite detailed. However, if you notice something, you are seeing a lot of big events, very big events. These events are so big that you can put Jupiter below them, like Jupiter can pass through this. That is why I said it's like observing a forest. You can observe big things quite easily. Sun is bright enough, big events are so powerful that you can easily observe it, no problem. But what is happening here? I can't do that. It's just gonna look like a bloody mess. That is the reason we are going so close to it, because these things again, they also play into role where these big spots are happening. So we have to understand these things. To understand that, it's like again, we want to understand the tiny minute details about that. We have to go closer. Then solar flares are very interesting to us simply because A, it can kill us. B, it can destroy us. C, it could give us pretty light. So that are the 3 categories of solar storm. So you can understand that it is a very high priority. We, as of now, we already have 1 or 2 satellites in Lagrange point just acting as an early warning system. But right now, those are very blunt instrument, and people will not take it seriously because we do not have enough accuracy about it. We may say, hey, shut down the grid just to protect us from a solar surge. But again, if it's a false alarm, 1 or 2 times we happen, that third time, even though the prediction would be correct, people will not trust it. So it's like we want to avoid false alarm. And if really bad coronal mass ejection happens, like a really bad one, it does happen every few years, and most of the time it misses us. But if really bad happens, and if it hits us, which has happened in the past, it's not something like happened in the dragon era. No, it happened past back, as in we used telegram at that time, and telegram, again, electrical wire, magnetic fields, it interacted with that and set poles on fire, buildings on fire. So you can understand that it was very violent. Now come to modern day, all our electronics are running on silicon. Silicon is ludicrously sensitive to this kind of spikes. It will destroy every single chip in the planet, or almost a half hemisphere can be destroyed by this. So you can understand that it is very serious threat to us. So we have to understand it, we have to analyze it before it hits us, so we can like properly analyze, target, and be like, okay, this shitty city or this continent is in the direct path, please shut down all your electrical grids so you don't end up in a fiery mess. So we have to study it, and we have to study before it comes to Earth, because by the time it's reaching Earth, it's already too late. And not to mention, all the processes that led to that event has already occurred. We have to observe how the heck it began, so we can get early warning instead of 10-20 minutes of early warning. We want like 2-3 days of early warning. That is why. And the final reality of every science, more data equals accurate prediction. The more we know, the better we can predict. As simple as that. So what we have learned so far, because the mission did happen in 12 August 2018. So on December 4, 2019, the first published work came out. And what does that mean? That simply means people have collected the data, they have processed the data, and new findings have been revealed, and those findings are credited to Parker probe. So that is what I'm classifying as what happened on December 4th. Now, Sun has a dust-free zone. We quote unquote knew that, but we did not know where that dust-free zone began. Why is that important? Again, it's very important simply because that dust is directly interacting with solar wind. You have to understand it. So to understand it, you have to understand where the heck it begins and where the heck it ends. So we know it does not end like because of voyagers and all that. We know how far it extends, but we do not know how where it begins. This probe flat out told us, bro, before this zone, like this closer to sun radius, there is no dust here. So that's a good start. We learned that, like we got this. Then we have another events aspect that we specified, that we can observe big solar events very easily. However, the smaller solar events that are like almost invisible to Earth's telescope, we started to observe them in the wide field photography in itself. And you can easily see in the side view, you'll see many tiny minute details that was flat out unobservable from the vantage point of Earth. So it has already started to give us a much higher resolution picture of sun itself. And then it became the first observatory to observe switchback. Basically, I specified the sun has a magnetic field that is very YOLO. So you have a magnetic field going like this, then it's switching back, then it's going like this, now switch back. Now there is a very interesting science behind it, but again, we knew quote unquote on mathematics, we knew how the heck it could happen, but we never observed it. This is the first time we observed it. So you can understand, only like it right now it is only like two gravity assist. It has to go to 7, so 5 are still remaining. So we have already started to learn so much. Every pass by, every flying mission, and if the probe lasts, let's say for 10 whole years, we can know so much more that further missions will help us. And not to mention, it will teach us. Basically, it's like putting a telescope, a microscope directly onto the sun. So it is quite amazing that what has it accomplished so far. And I am reasonably sure in the upcoming years, if it does not get destroyed, it's gonna do amazing job for us. So this was my presentation on Solar Parker Pro. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.